would like to evaluate the following double integral: x squared plus y squared to the 3/2, where our region is the top half of the circle of radius 5 centered at the origin. So if we were going to put this in rectangular coordinates, we would probably opt for vertical rectangles here, and then the integration would be dy dx. So our x limits would go from -5 to 5. Our y limits would go from y equals 0 to y equal the top part of the semicircle. And if you look, this is a very daunting task because this 3/2 power actually makes this impossible to integrate xy. So instead, this is a perfect candidate to switch to polar. Now, we know in polar coordinates that the equation of a circle centered at the origin is simply going to be r equal, in this case, 5. The theta limits, I'm going to start at 0 and go to pi. So my r, when I draw my little sector here, r is going to range from 0 to 5. Theta is going to range from 0 to pi. And when I translate this, we generally always put theta on the outside because theta limits are almost always going to be constant. I'd have 0 to pi. I'd have 0 to 5. This is r squared raised to the 3/2 power. And as we saw in the previous video, I replaced the dy dx with r dr d theta. Now that makes this quantity right here r to the 4th power. So when I integrate this, it's a fairly simple integration. I'm going to get 1/5 r to the 5th evaluated from 0 to 5 d theta. So 1/5 5 to the 5th, that's just 625. And because I'm evaluating a constant, it's just going to be 625 times the width of that interval. So 625 pi. So a relatively simple integration when I change to polar. Now let's find the volume bounded by z equal 36 minus x squared minus y squared, which is a downwards opening circular paraboloid that intersects the xy plane, which is the same as z equals 0. So we want basically this gumdrop shape to find the volume. Right off the bat, we'll go directly to polar coordinates because I have a circular base. Now, the circle will be where these intersect, and these will intersect exactly at x squared plus y squared equals 36. So I just add these to the other side and replace z equals 0. So we know in polar, this is equivalent to r equals 6. So in polar, I am looking at a circle just like before and saying, well, when I do this, my r is going to go from 0 to 6, and this time my theta is going to go from 0 to 2 pi. So our volume will simply be 0 to 2 pi, 0 to 6. In polar, this would be 36 minus r squared, and then I'm integrating that r dr d theta. So when I distribute this quantity right here, I'll get 36r minus r cubed. So now when I integrate this, I have 0 to 2 pi. I will have 18r squared minus 1/4 r to the 4th from 0 to 6 d theta. When I evaluate this quantity at 6, that will give me exactly 324 d theta. And like before, I'm integrating a constant, so it's just the constant times the width of the interval. So my final answer, 648 pi. So this fairly complicated problem once again became relatively simple when I changed it to polar. Now let's do one more. We would like to evaluate the following double integral. Now we can go ahead and integrate right now and substitute in the limits, but it would probably make for a very difficult integration. Not impossible, but difficult. So if I said, what is the actual region? Well, we noticed that y is going to range from -4 to 4, and x is going to go from 0 to the square root. And we recognize that's the right side of a circle of radius 4 centered at the origin. So if we switch over to polar, once again, this is a fairly simple transition. we would get, certainly for the r, we'd get 0 to 4. Now for the theta, I need one continuous interval for theta. Well, if that's 0 to 2 pi, then we should use pi over 2. We should use negative pi over 2 to pi over 2. That would express the right side. Now I will replace x with r cos theta, and then squared. I'll replace y with r sine theta, and then we throw in our r dr d theta. Now I definitely want to simplify this quantity. I would have an r squared, another r, another r. Okay, so that would give us r to the 4th, the square of the cosine, the sine, dr d theta. So at this point here, I'm only interested in integrating the r. These guys are treated as constants for the first integration. So that would give us the following. 1/5 r to the 5th cos squared theta sine theta, evaluated from 0 to 4 d theta. So when I raise 4 to the 5th power times a fifth, that would be 1,024 over 5. I'll go ahead and put that out in front since it is just a constant. And then that will leave us with cos squared theta sine theta d theta. So if I want to do a u substitution, or at least a version of a u substitution, I would clearly want my u to be the cosine function. Then my du would be negative sine theta d theta. So all I need is a negative sign. So I'll put a -1 right here, and then I'll put a -1 on the outside. Now my integral is of the form u squared du, so I don't actually have to change the variable. The integral of u squared du is a third u cubed. So this would give us negative 1,024/15 times the cube of the cosine function from negative pi over 2 to pi over 2. And if you notice, the cosine of pi over 2 as well as the cosine of negative pi over 2 are both 0. That means our final answer is actually 0. Now that seems kind of strange. It seems like it should be something other than 0. But if we go back and look at the integrand and look at my region, x squared is non-negative, but y is negative exactly half the time. So if this is my roof, it's kind of like saying half the time I'm above the xy plane, half the time I'm on the other side of the xy plane, and those essentially cancel. So now we have a good feel of how to integrate in polar coordinates.